Hello everyone, my name is Aritro and this is a joint work with Andrew Land from UMass Amherst, and we are excited to share with you our work on level noise. And in particular, in this paper we ask is a single question, which is do we really need goal samples for learning sample weighting strategy under level noise? So I'll start with the basic supervised problem setup. We have feature vector xi, we have level yi, and most cases we optimize some kind of risk function. In case of neural networks, it is mostly a cross entropy loss. So the problem is that what if we have a level noise? So that is yi can be noisy. So it is known that cross entropy loss is sensitive to level noise. And also it has been shown that neural network has enormous like memorization capability. So what it happens is that when you have level noise, it will have severely overfitting behavior, resulting in low test accuracy. So there are many directions, but I want to just show only two directions. There are like theoretically robust losses. For example, MAE loss, which is a symmetric loss, it has been shown to be robust to level noise. So if you optimize MAE with neural networks, it will be robust. But the problem is that it is not very friendly to optimize. So there has been a recent work where generalized cross entropy loss has been proposed. So the good thing about this is that it works as MAE loss in one extreme and cross entropy loss in other extreme. So you can trade off the robustness and optimization easiness. So the only thing you need to do is that just replace this cross entropy loss in this equation with some kind of robust loss. The other direction is sample weighting strategy. So what happens is that if there are noisy samples, you probably want to assign different weights for different samples, but you do not know which are noisy samples. But there are many heuristics. For example, if a sample has high loss, then probably it's a noisy sample. If some sample is very easy to classify, then probably it's a clean samples. So you can define some kind of heuristics function to assign weights and optimize this weighted classification problem. So a recent trend is to learn this function, because this heuristic is not scalable in most cases. So the idea is that you introduce a new datasets, which is a unbiased metadatasets, often called, and you optimize some accuracy on these metadata sets in a bi-level optimization problem, and you learn the weighting function. So recent works on these are these two, and they use some kind of meta learning based framework. But the main question we ask in this paper is that what if you do not have unbiased, clean, gold standard metadata sets? So what it comes down to is that we need to have this condition if we do not have access to clean datasets. So what it says is that we need to maintain the gradient direction from the metadata set. Okay, so this is our theoretical findings. So what we find is that suppose our meta samples are noisy, which is very easy to access, and we still optimize cross entropy loss. The only thing we need to change is that we need to introduce robust loss on the meta function, on the meta data sets basically. Yeah. So basically robust loss are not very easy to optimize, but the good thing is that this meta weighting function is actually a shallow network, and it's very amiable for MAE, and you get robustness for free. So this is the results we observed experimentally. So there are multiple settings. So what we find is that robust meta loss with corrupted meta samples, it performs much better than cross entropy loss with corrupted meta samples, and it performs exactly the same as the case when you have clean meta samples. So to answer the question that we started with, probably we do not need clean meta samples to learn the weighting strategy, but our results only hold for uniform noise. We observed similar kind of behavior on flip and flip to noise, but our theoretical findings only hold for uniform noise. So with that, I will end my presentation. Thank you.